Welcome, everyone. For today's prep, we're going to start looking at the chain rule. And this is a really important derivative rule. And what it does is it allows us to calculate the derivative of a composite function. So we're going to start by looking at, well, what is a composite function? And chain rule is important enough where I've broken this into a few separate sections based on kind of the pieces of our function. So we'll see ones involving power functions, trig or inverse trig functions, and then exponential or log functions. So it's going to be good to practice this because chain rule shows up all over the place. So first of all, what do we mean by a composite function? So let's get a little practice with that first, and then we'll jump into what this rule does. So all the derivative rules we've seen so far. We've seen the sum rule, we've seen the difference rule, we've seen the product rule, and we've seen the quotient rule. These are derivative rules that allow us to differentiate our way through an algebraic operation. So, algebraic operations, addition, subtraction, multiplication, division, it's a way to take two functions and kind of combine them together into a new function. Well, that's what composition is. So this is another way to kind of take two functions and combine them into one. But it's a little bit different than just regular addition or subtraction or those ones. So we say a function h is the composition of a function f and a function u if h of x is equal to, well, this formula. And the notation that we use for composition is this little open circle here. So the way we read this is function f composed with function u. And essentially what we do with this composition is we take our input x and we plug it into function u first. So we get u of x. And then we take this result and we plug it into function f. So when we do a composition, the function we plug into first is written here, and then the function we plug into last is written here. So the order's kind of a little odd there. But we call u of x, or we call function u, usually we call this the inner function because it's getting plugged into function f, and function f is a lot of times called the outer function because it's on the outside. So when we do this, we plug u of x into function f, so it's getting plugged into, so we call it the inner function. So you want to think of composition almost like an assembly line. So when we start with our variable x is the input. And the way the assembly line works is we plug it into function u first. So we plug it into the inner function u first, and we get this output u of x that we call u of x. Then we take this result and we plug it into the outer function, which is function f. And when we do that, we end up with the end result. So we take x, we plug it into function u, and then we take that result and plug it into function f. And so this whole process here gives us a brand new function, which we can call f composed with u. So you want to think of this almost like an assembly line. We take our raw material, our input at the beginning, and then it goes through function u. That gives us u of x. Then we take this new material, throw it through function f, and then we get our end product. So let's just see an example of what a composition would look like with some actual functions here. So example 1. We have a trig function, f of x, which is secant x, and then we have another function, u of x, which is x cubed, and we're going to calculate their composition. So we're going to calculate the composition where we take u of x and we plug it into function f. So in this formula, in part 1 here, u of x, or u is the inner function and f is the outer function. So in this case, u is the inner function and f is our outer function. And then in part 2, we're going to reverse the order just to show that the order actually does matter. So in this case, f is the outer function. All right, so the way we can do this is we take our formula for u, which in this case is u cubed, and we're just going to fill that in there. So we end up with f with x cubed plug in. And then we go to our formula for f, and the way we read this formula is it says whatever your input is, we're just plugging it into the secant function. So take your input and throw it into that secant function. So if we're plugging in x cubed, well, we're just going to replace each of these x's that we see here with an x cubed. So we would end up with secant of x cubed here. And this is the formula for our composite function. So when you look at this, we see kind of some x terms being plugged into another function. So we have our outer function, and then we have our inner function here. Now, for the second part, we're just reversing the order, because with composition, if you're doing an assembly line, if you start moving around the order in which you do things, you're going to end up with a different result. So composition, the order usually matters. Most cases it does. So again, we have our inner function, but now this is function f. So we're going to plug function f into function u, and u is now the outer function. And let's see what we get. And it's going to be a different formula here. All right, so first of all, what was function f of x? Let's go back up. F of x was secant. So we're going to plug secant x into our function u. And again, the way we read a formula is we're thinking of this x as just the input. So the way we read this formula is take whatever input you're plugging in and cube it. So in our case, we're plugging in secant x. So wherever I see an x up here, I'm just going to swap it out with secant x. So for our case, we're going to end up with secant x cubed. So it gets plugged into the cube function. So notice these are different. So the order actually matters. Here, the inner function is x cubed, and then with the one we just did, the inner function is secant x. It's being plugged into that cubed function. All right, so what we're going to see is chain rule helps us differentiate things like this, where it's not that we're adding and subtracting secant and x cubed. It's not that we're multiplying or dividing secant and x cubed here. What we're doing is we're taking x cubed and we're plugging it into the secant function. Or we're taking the secant function, secant x, and we're plugging it into the cube function. So we're not adding or subtracting or multiplying or dividing really here. This is kind of something else. And when we do this, it's going to be helpful to be able to identify when we have kind of the end results, be able to break that function apart into the inner and the outer function. So we're going to try the first two right now, and then we'll do the second two in class. But let's look at the first function here. We have x to the fourth plus 9x plus 3, all raised to the power 8. And we want to break this into two simpler functions. So when we look at this, kind of a tell for the inner function is whenever we see a nice big set of parentheses there with a whole bunch of stuff inside of it, the stuff inside of the parentheses is our choice for u. It's going to be our inner function. So, and then anything outside of the parentheses is our outer function. So our inner function is going to be this polynomial x to the fourth plus 9x plus 3. And our outer function in this case is going to be this raised to the power 8. So when we do this, let's call our outer function f of x, and we'll call our inner function u of x. So our outer function is, we'll call it f, and then our inner function, we'll call that u. And so for u of x, we're just going to take all this stuff that's inside the parentheses, and that's going to be our inner function. So the x to the fourth plus 9x plus 3. That's our inner function. And then imagine just kind of collapsing all this down and just calling this whole thing just a big variable. And actually, that's what we're doing. We could just kind of consolidate all of this and just call it u. So our outer function is raised to the power 8. Raised to the power 8. Now let's play the same game for the next one. So we have this composite function. So again, the tell normally for composition is parentheses. So if you see parentheses and then you see a whole bunch of stuff inside of it, well, that stuff inside of it is going to be your choice for u, the inner function. So our u of x, in this case, we want to think about what's the inner function and what is our outer function. So when we look at this, we see that we have that same kind of x to the fourth plus 9x plus 3 inside this nice big set of parentheses there. So that's going to be our inner function. So we're going to call u of x, x to the fourth plus 9x plus 3. That's our inner function again. It's literally being plugged into, it's inside of the sine function. So we just want to imagine then to figure out the outer function, which we'll call f of x. The outer function is literally everything outside of that inner part. So it's this sine, everything outside the parentheses there. So it's the sine function. And then we'll just give the kind of collapse this inner part down to a single variable. So really what we're doing with each of these is this is an assembly line where when we start with these functions, when we start with input x, the first thing that happens in this first formula is our input x goes into this inner function. And then that gives us something out, and then we take that result and plug it into this raised to the power 8 function, and then we end up with the final result. So we'll play the same game with the last two, but this is really the idea. And what we're going to see is chain rule is going to help us calculate the derivative for functions like this, where we have one function being plugged into another function. All right, so let's look at our chain rule. So we have, again, it's helping us differentiate a composite function. So when we look at this, we have our inner function, and then we have our outer function. And what this rule says is we kind of have to, the chain rule kind of helps us differentiate our way through the different layers of our function. So ultimately, we want to differentiate our way through all these different layers. So we have our outer layer, then we have our inner layer, and then we get into the middle there where the x is. So this chain rule is kind of helping us break through all those layers. So what we do is we start by differentiating the outer function, then we keep the inner function the same, and then we multiply that result by the derivative of the inner function. So it's going to be helpful when we're trying to differentiate a composite function like this to be able to identify, well, which is your outer function and which is your inner function. So again, the steps for the chain rule, we start by differentiating the outer function. So that's step 1. Differentiate the outer function. Step 2 is once we differentiate the outer function, we keep the inner function exactly the same. So u of x is going to stay exactly the same. And then the third step is we multiply that result by the derivative of the inner function. So here's our chain rule. Well, we're going to look at this in the context of a few special cases depending on what our outer function is. And the one we're going to look at right now is our power rule. So we're going to call this the general power rule, but this is really a special case of the chain rule. And this happens when the outer function is raised to the power r. So in our case here, we have this outer function, which is raised to the power r. And then we have our inner function, which is u of x. So what this chain rule says in the context of this power function is we differentiate the power function. So we do our regular power rule. So we bring down the r, put it in front. We subtract 1 from the exponent. And then we keep everything that's inside the parentheses exactly the same. And then once we're done with that, this is kind of the derivative of the power rule. This is kind of the derivative of the power function part. Once we're done with that, then we multiply by the derivative of the inner function. So if we're kind of going back to our chain rule, bringing down the r and subtracting 1 from the exponent is differentiating the outer function. Keeping u of x the same, keeping our inner function the same is, well, kind of like step 2 of the chain rule. And then multiplying by the derivative of the inner function, that's like step 3 of the chain rule. And like I said, this is just a special case when our outer function is a power function. So let's try an example to see how this looks. So let's look at that composite function we talked about. This x to the 4th plus 9x plus 3 raised to the power 8. So again, we went through and we figured out the inner function and the outer function here. So let's just kind of keep that in mind. So we have our inner function and then we have our outer function. So when we go to calculate the derivative here, we're going to call our derivative h prime. And the way this works is we're going to start by differentiating this outer function raised to the power 8. So we bring down the 8, and then we're going to keep what's inside the parentheses here exactly the same. So it's going to stay x to the 4th plus 9x plus 3. And then just like power rule, we're going to subtract 1 from the exponent. So we're going to go from 8 down to 7. So far, this part is just our regular power rule. We go from 8, put the 8 in front, and we subtract 1 from the exponent. And then we kept those terms exactly the same that are inside the parentheses. This is not the end of it, though. So far, we've only differentiated our way through this outer layer. Now we've kind of broken our way through, so now we want to multiply by the derivative of all those terms that are inside. So we have the derivative of our outer function times the derivative of our inner function. And then we just finish this off. So we have the 8. All this part we're done with. And then if we finish differentiating, now we've broken our way through. So it's just a polynomial. Now we just use our regular derivative rules. So the derivative of the x to the 4th is 4x cubed. Derivative of the 9x is 9. and then the derivative of 3 is 0. So there we go. We got our derivative. And when we do this, I want to see this kind of bracket prime step in our work to really emphasize that we're using chain rule here. So make sure you show this bracket prime step in your work. All right. So in class, we're going to try a few more examples like this and then go to the other special cases. So if we have trig functions or inverse trig functions, if we have exponential or log functions as our outer functions. So we'll see those in class. So we'll see you then. Bye-bye.